These class notes are actually not from your textbook. I think that this is a little bit of background information that you need in order to understand what's coming next in the textbook. They take a lot of things for granted in terms of sequence notation. So this is just a little section that I wrote called Intro to Sequences. The homework is not in my math lab. There's a worksheet at the back of this packet that is your homework, though I'm not going to collect it. It's just what you're going to use to practice. All right, so let's suppose you have a round, flat cake. So this is a mathematical cake. It's completely flat. It's not real. It has no thickness. Mathematical cake. Just a circle, yeah. So with one straight cut, you could cut the cake into two pieces, right? So if we have a mathematical cake and I cut once, it doesn't have to be through the middle, just anywhere, right? One straight cut, I can make two pieces of cake. Okay. How many pieces could you make if you made two straight cuts? 4. So I put them anywhere, right? Two straight cuts will give me 1, 2, 3, 4 pieces. Yes, but I wanted to know how the maximum number of pieces I could get. So yeah, I could just make 3, but I want to make as many as I can. Okay. So if I could make 3 straight cuts, how many pieces could I get? No. Play around with it a little bit. Take a few minutes. You can get more than 6. 3 straight cuts. So with 3 straight cuts, because they don't have to go through the middle, right? I could make my third cut go like this, right? My pieces don't have to all be equally sized. I just need to get as many pieces as I can. So I end up with 1, 2, 3, 4, 5, 6, 7. Yep. True. I don't care about the size. I just want to know how many I can get. How many pieces I can get. Size does not come into play here. So this is 1 cut, 2 cuts, 3 cuts. Okay, now I want you to try 4, maybe 5. See how many you can get, what the maximum number is. Compare with each other, see who can come up with the most. And then I want you to fill in a little table like this. Number of cuts, number of pieces. Okay, so we've already done, I think I just spelled pieces wrong. 1 cut made 2 pieces. 2 cuts, 4. 3 cuts, 7. I want you to be able to fill in 4 and 5 and hopefully find a pattern in this list so that you don't have to keep making drawings. So far we only have 3 entries. You might need 1 or 2 more to try to see a pattern. Okay, so for 4 slices, we have several people who've come up with 11. That seems like the most. So try to do this. 1, 2. Okay. And then to get the most new pieces, you want to cross every line that you've already drawn. So we're avoiding the intersection point, but even more than that, you're trying to make a new line that crosses all of the old lines. So if I put in a new line, say right here, now to put in my 4th line, I want to draw a line that goes through every other line that I've drawn so far. So something like I want to cross all 3 lines I've drawn. So maybe like that. A line that crosses all of the 3 lines I've already drawn. So I have 1, 2, 3, 4, 5, 7, 8, 9, 10, 11. So we get 11. Okay, a couple people were working on the 5, and I heard, what did people come up with for 5 lines? 16. Anybody get anything more than 16? 16 is right. All right, so what's the pattern? Uh-huh. So you're adding these to get this. Yeah. So you go the number of pieces you previously had, and then you add the number of cuts that you're making. Yep, so you just looked at this column and you said this one's +2, +3, +4, +5. So the number you're adding keeps increasing by 1. So you can see it two different ways. Yeah. Yeah, so some people can see the interaction between the two columns, and some people just look at the right-hand column and say, oh, these numbers are increasing not by the same amount every time, but by 1 more. Yeah. So all of our lecture today is going to be about identifying these kinds of patterns and the notation we use to write them down. So in English, we can say, well, add the number of pieces you have to the number of cuts you're making. That gives you your new number of pieces. Or we can say, well, you're adding 1 more every time you go up a cut, right? So we can say these things in English. You know, we're trying to express what the pattern is. But math has a very concise, and once you're used to it, really nice notation for how to express what this pattern is. So that's what we're going to learn about today, how to express these patterns mathematically. So a sequence is just a list of numbers. It can be finite, like this, 2, 7, 20. Or it can be infinite, like the set of all even numbers, 2, 4, 6, 8, etc. The numbers can be random, like in the first list. No pattern there, 2, 7, 20. Or they can have a pattern, like in the second example, where we could express what that pattern is. Well, there's only 3 numbers, and it doesn't go on, right? So these are just random. They're not, yeah. So we usually name a sequence with a letter. For example, if we want to talk about this sequence 2, 4, 6, 8, 10, 12, etc., we could name it the letter A, and we would say A equals this list of numbers. And we generally put sequences in those little curly brackets. All right, so A is equal to this list of even numbers. We name the terms of the sequence with a subscript. Okay. The subscript tells us where in the sequence to look. So if I ask you what A3 is, that means what is the third number in the list? So that would be 6. So A3 equals 6. So when I put a little subscript, that's telling you the place in the list. So what is A5? 10. Good. 5th number in the list. All right, so now we're going to try to establish how to write this pattern using our new notation with the letter and the subscript. Okay. So A2, what number is that? 4, okay. So what do I add to A1 to make A2? 2, right, yeah, or A1, yeah, so let's just say 2. Okay. So A1 is a 2, right? That's the first number in the list. What do I have to add to 2 to get the next number in the list? 2, yeah. All right, so A3, which is 6, right, is equal to A2, which is 4, plus what? 2, or A1, yeah. And then A4, which is 8, is equal to A3, the number right before it, plus 2. A5 is A4 plus 2. Right, so each number in the list is equal to the number before it plus 2. Okay, so A3 equals A2 plus what? Well, A3 is 6. A2 is 4. 2. There you go. Yes, awesome. So a sub n is equal to the number right before it. And the notation I use to, to represent the number right before a sub n. So all of these, like a3, a2, a4, a3, a5, a4, right? We just went decrease the subscript by 1. So the way you do that in general is subtraction. Take 1 away from the subscript and add 2 to it. So a sub n, this says in English that any term in the list is equal to the term right before it plus 2. Sure. So we established a pattern using these examples, right? And we said, well, A2, that's A1 plus 2. A3 is A2 plus 2. A4 is A3 plus 2. So each subscript, right? If I want A2, I take A1, right? And the way 1 is related to 2 is that it's 2 minus 1, right? So I have 3 and then 2, 4 and then 3, 5 and then 4. It's always 1 smaller. Yeah, so if for a general n, to reduce the subscript by 1, you write n minus 1. And then the 2's were always the same, so we have plus 2. So in English, right, so it really helps to use both the English version of what the pattern is and the mathematical notation for a while, so you get used to the notation. So this says that any number in the list, okay, we've represented that with a sub n. Any number in the list is, that's my equals, the number before it, the number right before it, that's the a sub n minus 1, that's the number right before any given number, plus 2. So our notation for any number in the list is a sub n. The number right before it is a sub n minus 1. This is called a recursive rule for a sequence. Okay, so we call a rule recursive if it uses previous terms in the list to calculate the current term. So if you have this n minus 1, right, if you say the previous term plus 2, or the previous term plus anything, that's called a recursive rule. So now I'm going to develop this list in a different way, because like you said, we can see the patterns, we can often see patterns in more than one way. Okay, so A1, what is A1? 2. Okay, so how do I write 2 as 2 times something? Yeah. And A2, what is A2? 4. How do I write 4 as 2 times something? And A3, that's 6. How do I write 6 as 2 times something? 2 times 3. And A4, that's 8, which would be 2 times 4. Okay, so what I want you to notice is this number that I wrote here is what I multiply 2 times, matches the subscript. 3, 3, 4, 4. So a sub n would be 2 times what? N. This is called an explicit rule, okay? Because I don't need to know the term right before it in order to figure it out, right? If I wanted to know A11, it would be 2 times 11, which is 22. So I can figure out any number in the list just by knowing its location. I don't have to know the number before it. So with the previous rule, if I wanted to know A11, I would have to know A10 and add 2 to it. But with this guy, all I have to know is the 11, the location. So this is called an explicit rule. If all you need to calculate the nth term of the sequence is the number n, in this case, you don't need the value of any previous terms. So these are just two ways of expressing the exact same pattern. All right, so let's play Guess My Rule. So I have a sequence here. So the list on top n is just the locations, right? So I have my list of SNs is what I'm really interested in. So what do you think S5 is? Yeah, how'd you come up with 7.5? Okay, great. Okay, so you are looking at the interaction between the two terms now. So you're looking at the n, and you're saying if you add n to half of itself, you get this, right? So n, which is 1, plus half of 1 is 1.5. 2 plus half of 2 is 3. 3 plus half of 3 is 4.5. Good. So S sub 5 would have to be 5 plus half of 5. 5 plus 2.5 is 7.5. That's another way to do it. Yeah. So you can just look at this bottom list and say to get from one term to the next, I'm adding 1.5. Which means 6 plus 1.5 would have to be 7.5. So what Faith was just explaining is that she was looking at the n, using the n to get the S sub n. So she said, well, when n is 1, you do 1 plus half of 1, which is 1.5. When n is 2, you do 2 plus half of 2, which is 3. 3 plus half of 3 is 4.5. So this one, where we do this plus 1.5, plus 1.5, plus 1.5, that's recursive, right? Because you need to know the previous term to get the next term. In this one, all you need is the n. So this one is explicit. This method is recursive. But we haven't actually written the rule down using notation yet. We're just identifying the patterns, the two ways of looking at it. All right, so using the patterns we've established, what would S sub 0 have to be? The number before 1.5 in the list. 0, right? Because to go forwards in the list, you add 1.5. So to go backwards in the list, you'd have to subtract 1.5. And 1.5 minus 1.5 would be 0. All right, so my recursive rule for S sub n not n, it's something plus 1.5. So S sub n is the nth term in the list. Any given term is equal to the term right before it. Yes, the term right before the nth is S sub n minus 1. You have to be really careful with the subscripts. You have to write it neatly so that you can see that the n minus 1 is all in the subscript. Right, at the same height. Yes, because it's easy to confuse S sub n minus 1 with S sub n minus 1 if you don't write it well, right? You have to make sure that this n minus 1 is clearly in the subscript. Not the same. So this is my recursive rule. Sometimes it helps to write this out in English before you try to write the symbols. Like recursive rule, I would say any term is the term before it plus 1.5. Then try to translate it to symbols. Okay. So any term, we write S sub n. Okay, so n stands for like any term. Yep, any term. Is the term right before it? So is the equal sign, right? The term right before any term, right? The term before it, that's s sub n minus 1. The term right before the nth is one less than the nth. So like the term right before the 5th term would be the 4th. The term right before the 12th term would be the 11th. So that's where the minus 1 comes from. Okay. And then plus 1.5. So the important notation is that S sub n or A sub n or B sub n, whatever your sequence is named, that's how you represent any given term. And the term right before it will be S sub n minus 1. What would the term 2 before it be? The term 2 before it in the list. Yes, so the term 2 before any term would be S sub n minus 2, right? 2 before it. So A5, 2 before that would be A3. A8, 2 before that would be A6. So you subtract 2 from the subscript to get the term, not behind it, but the one behind that. All right, so now an explicit rule for S sub n. So that's how you were looking at the pattern before. So we were saying S sub n equals, and this time I'm not allowed to use the term before it, so I can't use S sub n minus 1 in this rule, because this is explicit. The only thing I'm allowed to use is n. No, because yeah, that's one way. Yeah, that's good. So if you do 2n minus 0.5n, what do you get when you, those are like terms, right? 2n and 0.5n. What do you, 1.5. 2 minus 0.5 is 1.5 n. So we can if we can check it.
I didn't.
Right. Yeah.
I had to like take it out.
Yeah. So now if I wanted to say what's S sub 4, right? I would say, well, 1.5 times 4, right? Because I've given the n in the subscript. 1.5 times 4, that is 6. Go up to my table. When n is 4, S sub n is 6. So I know my formula is right. So you can always check your formulas. Maybe we'll do one more. If I wanted to do, say, S sub 2. According to my formula, I would do 1.5 times 2. 1.5 times 2 is 3. And that is what my table says S sub 2 is.
So recursive is pretty much like finding a pattern and explicit is a formula.
They're both formulas. Yeah, they're both formulas.
So recursive defines the pattern.
Yeah.
Explicit in the formula. And so if you have to print the right,
Yes.
And
N.
you don't have to worry about it. Not in relation to S sub n. It's the changes in n.
Yes. Yep. All you need to know to write, they're both different kinds of formulas. So I think that you're using the word formula in the fact that you've been trained to think a certain kind of thing as a formula. So and that looks like this, right? So this is the kind of formula you're used to seeing. Okay. So this, my recursive formula, right? That's also a formula. It's just a different format than you've seen before. And it's just called a recursive formula. So it's just looking at patterns in two different ways. Okay, so this is a special kind of sequence. Okay, a sequence where the rule to get from one term to the next is to add or subtract a constant. It's called an arithmetic sequence. Okay, and this is arithmetic because to get from one term to the next, I'm always adding the same number, 1.5. So think about the cake cutting problem. Was that an arithmetic sequence? No, because we were adding a different number every time. 2 and then 3 and then 4 and then 5. Not the same number. Okay. So the cake cutting problem is not arithmetic. This one is arithmetic though. We're to add the same number, a constant, right? The same. All right, another game of Guess My Rule. So this time I want you to just discuss in your groups. Try to work through this sequence G sub n and the questions about it. Okay, so what do people come up with for G sub 5? 80, yep. And how did you know that? The pattern is doubling, so times 2. 5 times 2 is 10. 10 times 2 is 20. 20 times 2 is 40. So if I continue that pattern and multiply by 2, the next number should be 80. Okay, so what number, if I were to go backwards in the list, right, what number would have to come before 5 in order to make this pattern continue? 2.5. So I would have to ask myself, well, what number, when I double it, would give me 5? And that would have to be 2.5. So it's a little weird to write G sub 0 because we call the subscript the place in the list. So G sub 1 is the first number in the list, so it doesn't quite make sense to say what is G sub 0 because it's the 0th number in the list. But you just go with, well, if this is the first number in the list, the 0th number would be the number before it, which is a little weird.
Think about it on the graph, because she's like, well, it's not -1. Think about it as far as a graph, it makes sense to me.
Okay, good.
Try and think about it like
Yeah.
as a number. I'm like,
Yeah, it's a little abstract. Mm-hmm. Mm-hmm. Yeah. All right, so we got G5 and G0. A recursive rule, right? So maybe it would help if we write it in English first. Any term in the list is double the term before it. Right? So 40 is double 20, 20 is double 10, and 10 is double 5. Okay, so if I want to write this in symbols, I would write G sub n is double, that's 2 times, right? And then how do I write the term right before the nth term? Yep, G subscript n minus 1. Okay, so let's do some non-generic examples. Like if I did G sub 4, right? That's 40, right? And that's 2 times 20, 2 times the number right before it in the list. So that's 2 times the number right before it in the list is named G3. I already did the minus 1 in my head, right? 4 minus 1 gives me 3. Yeah. So if I wanted to make this generic, right? Or let's do one more. Let's say G5, which is 80, right? That's 2 times G4. 2 times 40. Okay, so my subscript 4 and 3, or 5 and then 4, they're different by minus 1. One is 1 smaller than the other.
Do you always use a subscript to make that n-1?
Yes. Yep, that's where the n-1 comes from.
Just the n place,
Yes.
drop to n, do G2,
Yeah,
right?
that would be 2 times G1.
And so then, what G, or the two will be in,
Mm-hmm.
so that's the place.
Yes. Good. Good summary. She said the subscript is the place in the list, right? So to find G sub n, like to find the value at any given place in the list, right? N is just representing some place in the list. You always do 2 times the place right before it, right? And the place right before it, right? If n was 8, the place right before it would be G7, right? So you always do minus n-1 to get the place right before it.
So 8 minus 7 is 1.
8 minus 1 is, yeah, 8 minus 1 would be 7.
Right. So
Yeah.
when you're doing that, it's I'm seeing it as if you write G5 equals 2 times G4. So it's 5 minus 4 equals 1.
That's how
Yes.
So then that's like
Uh-huh. Yep. And G4, instead of writing as 2 times G3, you could think of it as 2 times G4 minus 1, which is G3. Yeah. Okay, now the explicit rule is the trickier one here. So I'm going to write this list out vertically because it's going to help us visualize the pattern here. You use whatever problem-solving technique works for you. I'm just showing you one that works for me.
see it.
You see it? What is it?
Oh, I see it my way.
Okay.
I see the 5. Oh, so you multiply, right? So 5 times 2 is 10.
Uh-huh. Still recursive because you're using the previous term in the list. So to get to the 20, you're using the 10, right? You're not allowed to do that for an explicit rule. All you're allowed to use is the n.
Well, I see 5 times 2 is 10.
You can't use the 5, right?
Okay.
Right. All you can use is the n's. So let's look at the 10, right? So 10 is 5 times 2, right? So I'm going to write this as 5 times 2. And 20 is the 10 times 2, right? But instead of writing the 10, I'm going to use the 5 times 2 times 2, right? Instead of writing 10 times 2, write 10 as 5 times 2. I'll write the whole thing out. So 20 is 10 times 2, which is 5 times 2 times 2. And then 40, right. 40 is 20 times 2, but 20 I can write as 5 times 2 times 2. So this is 5 times 2 times 2, that's 20, times another 2 to give me 40. And then the 80 I can write as 40 times 2, but 40 can be written as 5 times 2 times 2 times 2, then times 2 again to give me my 80. Okay, so repeated multiplication, how do we denote that mathematically? Exponents. Good. So this one, just going to make this a little clearer. So I'm purposefully ignoring the first entry for a minute here. But when n is 2, I have 5 times 2 to the first, right? Because multiplying by 2 once is 2 to the first. And when n is 3, I have 5 times 2 squared. And when n is 4, I have 5 times 2 cubed. And when n is 5, I have 5 times 2 to the fourth. So what would the first entry have to be here if I follow? No, because the second entry is 5 times 2. No, because I'm not raising 5 to any power. I'm raising 2 to powers.
So if
It's just 5. Yeah, right. I already knew that. But how could I write it as 5 times 2 to the something? No, the next end, 5, 0, right?
Wouldn't that be 0?
No, any number to the 0 is 1. You guys don't remember this from Math 105? Let me just remind you. So if I have 2 to the 4th, 2 cubed, 2 squared, 2 to the 1st, 2 to the 0. Right, yes. So 2 to the 4th, that's 2 times 2 times 2 times 2, which is 16. Yeah. And 2 cubed is 8, 2 times 2 times 2. 2 squared is 4, 2 to the 1st is 2. So the pattern in this list is that I'm dividing by 2, right? 16 divided by 2 is 8, divided by 2 is 4, divided by 4 is 2. 2 divided by 2 is 1. So 2 to the 0 has to be 1. Okay. All right, so when I come back over here, I've written all my entries now as 5 times 2 to the something. So what I'd like to do now is say for a random n, right? It's going to be 5 times 2 to the something. And the question is, what should that something be? It has to be related to n to make an explicit rule. Say it again. N minus 1. So explain why it's n minus 1, please. Yeah, so when n was 1, my exponent was a 0. And when n was 2, my exponent is a 1. When n is 3, my exponent's a 2. N is 4, exponent's a 3. N is 5, exponent's a 4. So my exponent is always 1 smaller than n. So it's going to be n minus 1. No, I just did that to say what should go there. So my explicit rule would be g sub n is 5 times 2 to the n minus 1. And we can check it, right? So let's check one. If I do g sub 4, that says that this should be 5 times 2 to the 4 minus 1, which is 5 times 2 cubed, which is 5 times 8, which is 40. Is G4 40 in my list? Yes. So this is another special kind of sequence. A sequence where the rule to get from one term to the next is to multiply by the same number. Right? So if we're always multiplying by the same number like we are here where it was times 2, that's called a geometric sequence. You got it. Yep. All right, so I want you to go back to the cake cutting problem. So remember we had number of cuts. This is going to be our n. And the number of pieces we could get. Oh, it's IE. Definitely IE. Number of pieces, that'll be P sub n. And we had 1 cut, 2 pieces, 2 cuts, 4 pieces, 3 cuts, 7 pieces, 4, 11, 5, 16. I want you to try to write a recursive and an explicit formula for the number of pieces given the number of cuts. A recursive and an explicit formula for this rule. The recursive rule is coming a little more naturally in this case for most of us. So we're saying, well, P sub n. All right, so wait, I'm going to practice what I preach here and write it down in English. So each number in the list, or any number in the list, right? Each number in the list is the number before it plus, okay, so one of the patterns that we saw before was using the previous number, right, was this sum. 2 plus 2 gives me 4. 4 plus 3 gives me 7. And 7 plus 4 gives me 11. Oops. Right. So the 11 is the previous number in the list, the 7, plus my current value of n, the 4. Yeah. Plus, so each number in the list is the number before it plus the value of n. So the number that I'm adding is the subscript. Okay, so if I want to write this in mathematical notation, I would say P sub n is the number before it in the list, P sub n minus 1, plus n. And then you can check recursive lists, recursive formulas, the same as you can check explicit formulas. So let's say I want to find P5. I want to check that it gives me 16, right? This says take the previous number in the list, that would be P5 minus 1, and add 5 to it, right? Because my n is 5 in this case. So I'm replacing all my n's in my formula with a 5. This n becomes 5, and this n becomes 5. Yep, so this says P5 is P4 plus 5, and P4 is 11, which is 16. So I get the right number. Okay, so explicit formula is trickier, right? So I'm going to start with the number 2, and then I have to add plus 3 plus 4 plus 5 plus 6. Oops, I did that wrong. Those are all off by 1. Plus 2, 3, 4, 5. So I start with 2 and I add 2 to it. So 2 is sort of like my base, my foundation, the first number in the list. Okay, and then I'm going to add 2 to it, and then 3 to it, and then 4 to it. And how many of these numbers, how many times do I have to do that? So when I'm trying to get to the second number in the list, I added just the 2, right? And when I try to get the third number in the list, I have to add plus 2 plus 3. And when I get to the fourth number in the list, I have to add plus 2 plus 3 plus 4, 3 different numbers. Right. Yeah. So I have to add n minus 1 of these numbers that I'm adding on. So to get to the fifth number in the list, I had to add plus 2 plus 3 plus 4 plus 5, right? So I'm going to add 2 plus 3 plus 4 plus up to n. So this is not the prettiest explicit formula. In fact, it's a little crazy. It's a hard one, for sure. Don't worry about it if it's a little tricky. So let's see. Let's just check. Let's do P4. That says start with a 2, and then start adding 2 plus 3 plus 4 up until I get to n. So I have plus 2 plus 3 plus 4. 2 plus 2 is 4, plus 3 is 7, plus 4 is 11. So let's say I wanted to find P6. Okay, according to my recursive rule, That would be 22. Yeah.
No, like, let's see, 2 plus 2.
So you start with a 2, and then you add to that 2 plus 3 plus 4 plus 5 plus 6 plus 7 until you hit n, the subscript on your p. Yeah, the subscript on your p, whatever you decide n is. So if you want to do p6, for example, you start with a 2, then you add 2 plus 3 plus 4 plus 5 plus 6. You stop once you hit the subscript. So that would be 4, 7, 11, 16, 22. Yes. Yeah, exactly. And a 6 in that formula. Yes. Yeah. Yeah, it's not a nice formula. It's weird. Yeah. It's a weird formula. Explicit, yes. Because it only has n in it, not p sub n minus 1. That's what makes it explicit.
I'm like, what?
Okay, we only have like 5 minutes, so we can't really do this activity. How about instead, you can start on the worksheet at the end of the packet.